Hello, everyone, and welcome to our ninth lecture of GPU computing. Today we'll be talking about a new parallel pattern, which is stencil. So last time we looked at convolution, and with convolution we introduced a new feature, which is the use of constant memory. And convolution is the pattern where every output element was some linear combination of the corresponding input element and the elements around it. And usually that weighted sum is defined by some kind of convolution kernel. We called it a mask just to avoid overloading the word kernel to mean multiple things. So we had this convolution mask, and the way that we applied to this patch of input to get some output. And the way we parallelized it is by simply having one thread assigned to each output element, and that thread was responsible for looping through the input elements and the mask and doing the weighted sum and then storing the output result. And we said that since this mask is all and is constant, we don't change it, and it's accessed by all threads in the grid, a good place to put it is somewhere called constant memory. And we saw how all the threads in the grid have access to this constant memory, and that there's actually a constant cache in the hardware that is very fast, and it's used to cache all this constant memory. So that allowed us to avoid the global memory loads when we access the mask. So we put the mask in constant memory. And then we also observed that the input that was in global memory, we saw that a thread block that was computing a particular output, the elements within that thread block actually had a lot of common input. And so what we did is we decided to load the input tile into shared memory, and then the threads computing the output elements will go through shared memory when reading from the input tile. Now, one tricky thing about this was the fact that the size of the input tile dimension, was different from the size of the output tile. So what we did is we ended up launching enough threads per block in order for us to be able to load all the input tile elements in parallel. However, when we came to actually compute the output tile, we ended up only using a subset of these threads to compute the output tile. And then finally, we said that if we are at the boundary, the elements that are outside of the boundary should not be accessed when we are loading from global memory to shared memory. So what we did in this case is instead of because we cannot load anything from here because these elements don't exist, we instead load zeros into store zeros into shared memory, and that way when we do our local loop through the mask and the input shared memory tile in the input tile in the shared memory, we don't have to worry about boundary conditions here because we know that anything in the input tile is valid. So this was a quick overview of what we covered last time, and I hope you guys enjoyed the assignment on where you had to implement this. We didn't do the code for for tiled convolution last time because you guys were implementing it. So any questions about what we covered last time before we move on to today? All right, if no questions, then we will look at another parallel pattern, which is stencil, so stencil computation. What is a stencil computation? A stencil computation pattern refers to a class of computations on a structured grid where the value at a grid point is computed based on a subset of the point's neighbors. So for example, if I have a grid of points, this for example could be a 2D grid. A 5-point stencil on a 2D grid is an operation where the next value the next value at some grid point is the combination of that grid point and then also the neighboring elements in the grid. And we can also do this in 3 dimensions. So we can have a 7-point stencil in 3 dimensions where the next value of the grid point is based on the value of the grid point and its neighbors in the x dimension, the y dimension, and also the z dimension. Okay. Now, what I'll do in this lecture is I'll kind of alternate between 2D and 3D. We're going to focus on 3D in the implementation. However, we're going to use 2D for some of the illustrations just because it's much easier to illustrate certain concepts with 2D. So I'll be alternating between 2D and 3D. So if I have a 2D 5-point stencil, I basically have a grid of points. Here I show a 4x4 grid. And in the output grid, this element here in the output grid is going to be based on the corresponding elements in the input grid and the elements that neighbor it in the input. Okay. Now, typically, these grid points are conveniently stored as 2D arrays. So we can think of the stencil computation as we can think of the output as being a 2D array of grid points. And for each of these output grid points, they will be based on the corresponding input grid point and the neighbors to the above, below, to the left, and to the right. Okay. And the same thing applies in 3 dimensions. So in 3 dimensions, the output grid point is going to be based on the linear combination of the neighboring input grid points in the x dimension and the y dimension, and then also in the z dimension. Okay, so we typically store these output 3D grids as naturally a 3D array. Store these output grids as 3D arrays. Okay, and over here, yeah, you'll see things are a little bit more difficult. Is that each element here, this element is going to so this output element is going to be based on the corresponding input element, and then the neighbors in the y dimension and the x dimension, and then also in the z dimension, which you don't see. Over here, this for this input element, it will be based on this input element and the neighbors in the x dimension, and then the y dimension, which you don't see, and the z dimension. And then over here, this element over here is going to be based on the corresponding element to the input and the neighbors in the x dimension, which you don't see, and then the y dimension, and then the z dimension. Okay? And just to visualize what I mean by the three-dimensional storage. So here, for any grid point over here, its value is going to be based on the corresponding elements in the array in each of the dimensions, so the x dimension and the y dimension, and here also the z dimension. If you can think of some of the points in the inside of this cube that we don't see, this is what its access, the elements that access will look like. Okay, does somebody have a question?
Yes. Is there a difference between this and convolution? Because it seems
that is an excellent question. That is an excellent question. Thank you for that. And the answer is that stencil is actually very similar to convolution. Stencil is actually a special case of convolution. So you will see today that a lot of what we did for convolution, we're also going to do with stencil. But some differences between stencil and convolution include well, when we did convolution, we did a 2D convolution. So today in class, we're going to do a 3D stencil, just because we haven't yet practiced using 3D grids and accessing 3D data. So this is one difference that we will have, but we could have done a 3D convolution if we wanted to, and we can also implement a 2D stencil if we wanted to. But there are some special things about stencils, like the fact that usually with a convolution we assume that the whole block surrounding the input element is what I would like to access. However, with stencil, usually it's not the whole block. Usually it's only some subset of those neighbors in the whole block. And what that does is that it enables some optimizations that may not necessarily be possible with convolution. And we'll see an example of those optimizations. Okay, but it's an excellent observation that yes, this is very similar to convolution. Okay, so how do we paralyze stencil? Well, this is what we had seen before. We have our output grid where every element corresponds to the value at each output grid is some combination of the value of the grid and some of the neighbors. So how do you expect that we might go about paralyzing something like this? What is kind of the most fine-grained and obvious way to do it?
Just like convolution, output a thread to every output element.
Right, exactly. So just like convolution, we can assign one thread per output grid point, right? So we divide our output grid into these 2D blocks, and inside of each 2D block is going to be responsible for a set of threads, and each thread in the block is going to be responsible for one of the output grid points, okay? And naturally, since this is 2D, we're going to use a 2D grid of threads. Now, one thing I'm going to do is I'm going to make a simplifying assumption that we're going to carry out throughout the course. To simplify the way we deal with boundary conditions, okay, what we're going to do is if we have some input array, we're only going to compute the stencil for the internal output values, not the values of the boundary. And what this does is that it ensures that the input values that we access are always inbound. Okay, so what I'm going to do, when I'm going to paralyze the stencil and I'm going to do the computation, I'm not going to calculate the output value at the boundary element. I'm only going to calculate the output value in this green square, this green part of. Okay, and the nice thing about that is that we don't have to worry about doing a boundary check when we access our neighboring inputs, because the neighboring inputs will always be inbound. Okay, and this assumption is usually a valid one, because a lot of times when we do a stencil computation, these neighboring elements are actually elements that are computed maybe somewhere else, and then they're, maybe I'm parallelizing this across many GPUs. So usually some other GPU might be responsible for computing these halo elements and sending them to me. So this is a reasonable assumption to make. Okay, this will just simplify our code when we're writing, because we're going to have enough to deal with in our code in terms of indexing and boundary checks. So just to simplify that, we're going to make the assumption that we only process the internal input elements, and therefore so the internal output elements, and therefore our input elements are always inbound. Okay. So if we move on to paralyze 3D stencil. So if I want to paralyze a 3D stencil, remember we have a diagram here where my 3D stencil, sorry, my output grid was a 3D array and my input grid was a 3D array. Okay, so how would we paralyze this? The 3D case of stencil? What's the most fine-grained and obvious way to do it?
A cube.
Right, so I think what you mean by that is a 3D grid. So yes, so the most obvious way to do it is to assign one thread per output element, and naturally for that we would need to use a 3D grid of threads. Okay, so let's go and implement this stencil using a 3D grid of threads. Let me switch to the code. Okay, so this over here is the code for stencil computation. I've already taken care of allocating the input and the output, and here we're gonna have the input and the output, and the whole space is going to be n by n by n. Okay, so the input is going to be n by n by n. The output is going to be n by n by n. We allocate, we do the copy, and then over here, this is something that we haven't seen before. What we're going to do is we're going to create a 3D thread block. So here the thread block is going to be block dim by block dim by block dim. Okay, and then we're also going to create a 3D grid of blocks where in every dimension we're going to have the ceiling of n over blocks. Okay, and in this case, since I have a 3D block, because if I have an 8 by 8 by 8 block, then that is a total of 512 elements, 512 threads in the block. And remember that the maximum number of threads on a typical GPU nowadays is usually 1024 threads per block. Maximum number of threads per block is typically 1024 threads per block. So 512 is the best we can get if we want to have a number that's the perfect cube. Okay, so having now launched this stencil kernel, the next step I would like to do is I would like to do the computation. So the first step is finding what element the thread is responsible for. Okay, and we're going to use I to indicate the z index in the z dimension, J to indicate the index in the y dimension, and K to indicate the index in the x dimension. Okay, so how do I start? Well, I start by calculating I, J, and K. Okay, I can write unsigned int I is equal to block index dot x times, sorry, not dot x dot z, remember, I is in the z dimension, times block dim dot z plus thread index dot z. Okay, now as you can see, extending to a three-dimensional grid is not that hard. It's very similar to what we did before, but we just have dot z in this place instead of dot y and dot x. Okay, and we're going to do the same thing for j and k. So j is going to be block index dot y times block dim dot y plus thread index dot y, and then finally k is going to be block dim block index dot x times block dim dot x plus thread index dot x. All right, so now that we have our indices, the next step is to perform the stencil computation. Now remember what I said before. What I said before is that we're going to simplify the boundary conditions by only computing stencil these internal output elements. So anything at the boundary is not going to be computed, and the same thing applies for our 3D stencil. Now here I know that I have these elements at the boundary colored, but that's because I wasn't able to show you the elements that are inside of this cube in the illustration. However, these elements will actually not be computed in the output. What I will be computing is the elements that are inside of this cube, where all their neighbors are going to be inbounds in the input. Okay, so to make sure that I'm doing only the internal elements, I'm not going to process the elements whose index is 0, and I'm not going to process the elements whose index is n minus 1. Okay, so the boundary check is going to be if I is greater than or equal to 0, okay, and sorry, not greater than or equal to 0, greater than or equal to 1, okay, and I is less than n minus 1. So usually we used to have I greater than 0 and I less than n. This time we have I greater than or equal to 1 and I less than n minus 1 because we're ignoring the elements at the boundary, the output elements at the boundary. Okay, and we want also j to be greater than or equal to 1, and we want j to be less than n minus 1. And of course, over here, n is the number in all 3 dimensions because I'm assuming a square grid for the whole stencil space, but it may not be the case. You could have an example where it was not a square universe that you were simulating. Okay, and then finally we're going to do the same thing for k. So k greater than or equal to 1, and k is less than n minus 1. Okay, so now that I have this boundary check that makes sure that I'm processing an output element that's inbounds, what remains to for each output element compute the some linear combination of the input elements that surround it. Okay, now first let me so I'm going to do out of the element is going to be equal to some combination of the input element. Okay, now let's see first calculate the index of the output. Okay, if I want to calculate the index of the output, my indices I, J, and K, and this input output was dynamically allocated, so it's a linear array. So I need to take my three indices I, J, and K and convert them into a linear index to access this whole 3D array. Now we saw how to do that before with 2D arrays. We basically did the row index times the width plus the column index. And we're going to do something very similar for 3D arrays. Over here, this array is also going to be major order. And the way that works is we store this first row over here, followed by the second row over here, all in the same plane, followed by the third row over here, followed by the fourth row over here, until the last row down here. And that means we have all these elements in this first plane consecutively to each other. And then we go to the next plane and we put the first row, followed by the second row, followed by the third row, etc. And then we store the next plane, and then we store the next plane, and then we store the next plane, etc. Okay. In order for me to figure out the index of my element in the 3D array, I'm going to first take I. I is going to tell me which plane I'm computing. Okay, and I'm going to take I, and I'm going to multiply it by the number of elements in a plane. Now, how many elements do I have in a plane? If I want to start, if I want to compute in this plane, how many elements do I skip to get to this plane?
I times n squared.
Right, exactly. It's going to be I times n squared because every plane is going to be n by n. So I'm gonna go to the ith plane is going to be start at I times n squared. So n times n. Okay. Then plus now that I'm in the plane that I care about, I wanna go to the row that I'm gonna care about. So j is going to be the index of the row. So I'm gonna do j times and is what? Well, it's going to be j times the size of a row. What's the size of a row?
N plus k.
Well, the size of a row is going to be n, so I'm going to do j times n. And then, as you said, then we want to go to the element in the row that we want, so the index of that is going to be k. So then it's going to be k. So it's going to be I times n plus j times n plus k. Sometimes people also like to write this as I times n plus j times n plus k. So over here, I times n plus j, and then you have a times n. So here you end up multiplying I by n squared. Here, the way you're reasoning about it here is that you have you go to the ith plane, and then you multiply by n to get j. So this whole thing now is the index of your row in the three-dimensional space, and then you multiply the index of the row by n, and then you add k to get to the offset of the. Okay. So now that we have indexed our output, let me just for consistency do it this way. And now that we have the index of the output, the next step is to go to the inputs that we want. Okay. Now for every it's going to be some combination of the input and the neighbors in the x, y, and z dimension. So what I have over here, what I've done is I've defined two constants, C0 and C1. And what we're going to do is we're going to multiply the corresponding input element by C0, and then we're going to multiply all the neighbors by C1, and we're going to add them. Okay. For different applications, these constant values that you multiply the neighbors with and the input itself with are going to be different. But here we don't really care about a specific application. We're implementing an abstract version of Stencil, but depending on your application, these constants that you have might have different values. Okay, so I'm going to multiply C0 times the corresponding input element. Well, that's just going to be n of, and then I'm going to use the same index. And then I'm going to do plus, and then next what I'll do is I'm going to multiply C1 times all the neighboring elements. I'm going to have parentheses over here, and I'm going to put all my neighboring elements down. So the first neighbor, so the neighbors in the x dimension are just going to differ by k. So rather than having k, I'm going to have k minus 1 and k plus 1. So my neighbors in the x dimension are going to be n of I times n plus j times n plus, and rather than having k, I'm going to have k minus 1. So this is so if this input, this dark blue cube in the middle is ijk, then ijk minus 1 is going to be this cube over here, this element over here. And then I'm going to also add. I will also add of ijk plus 1. So that's going to be the cube over here. So I have k minus 1 and I have k plus 1. Okay, and then I also want to add the neighbors in the y dimension are going to be this one, j minus 1 and j plus 1. So we'll do that. I'm going to write n of, and this time it's going to be the same k, but I will have, instead of j, I'm going to have j plus j. We start with minus 1 just for consistency. Minus 1. And then I will also have j plus 1. This is j minus 1 and this is j plus 1. And then finally, I want to have the neighbors in the z dimension. So that's going to correspond to I minus 1 and I plus 1. So over here, rather than having j plus 1, j minus 1, I'm going to have j and k as is. But then over here, I will have I minus 1, okay, and I plus 1. Now, of course, you don't have to put each of them. Oops, I need to also, obviously, I need to be doing the addition each time. Of course, you don't have to put them all on a different line. I'm just doing that to make it easy for you guys to see what's going on. So I don't have a very, very long line. Okay, so I have the input element multiplied by C0, and then the neighboring input elements in the X dimension, the Y dimension, and the Z dimension, all added together and multiplied by C1. Okay, so this would implement a kind of initial version of Stencil. Any questions?
Professor, are C0 and C1 like the weights?
Yes, C0 and C1 are sub weights. They will be different depending on what your application is. Okay, what your application is.
Where were they defined though?
I defined them in common.h.
Okay.
Okay, yeah. So you maybe you hard code it. Maybe this is I don't know what you can just put a constant here if your application is always going to use the same constants.
Professor,
Yes?
can you repeat what's C0 and C1? I didn't understand.
So, like I said, the definition of stencil is that every element is a combination of every output element is going to be some linear combination of the input element and its neighbors in each dimension. Okay, so here what I'm doing is the output element is going to be C0 times the input element plus C1 times each of the neighbors. Okay, and what the values of C0 and C1 are depends on the application. But here we're just implementing some abstract stencil. So what their values is doesn't matter.
Yeah, C0 and C1 would represent, for example, if it was a convolution, a mask, the values of a mask. Right?
Perhaps, but this isn't a convolution because a 3D convolution would not just have the immediate neighbors. You would also have a whole cube around centered around the end.
Okay, but they would be 0. Okay.
But I mean, you could implement this as a convolution where all the other elements in the cube are 0, but that wouldn't be an efficient way because you'd be doing a lot of multiplications by 0. Okay.
Sir, I have a question.
Yes.
If we have more than 7 elements around the input, do we have to write all the indices, hard code them, or is there another way, like a formula or something?
Yeah. So typically, yes. If you had like if you have more just like a 13-point stencil where you want 2 elements in each dimension, which exists, then yes, you would have to hard code all of those. But the more and more dense it becomes, the more it looks like a 3D convolution. But usually stencils aren't that dense around the input. But yeah, if you go further, if you go 2 elements in each dimension, then yes, you would have to write those in here somehow.
Okay, thanks.
Yeah, you're welcome. Okay, so let's run this and see what kind of performance we can get. So I'm going to compile, and I'm going to run. Run on the CPU, then it's going to run on the GPU as usual. And this is the performance that we get. We have 24 milliseconds on the GPU for just the kernel, 500 with all the copy time. Because remember, this is a cube, so this is really huge. I'm doing a 512 by 512 by 512 cube, by the way. And then the time on the CPU is around 2.2 seconds. Okay, so we have almost 100 times speed up if we are looking at just the kernel. Okay, not so much, maybe 4 times speed up if we're including the copy time. Okay, so this is the code that we just wrote. And now that we've written this code, the question is, what optimizations can we apply? So what optimizations come to mind? Any suggestions?
Tiling, actually.
Tiling, right. Tiling, exactly. So the first optimization you might think of is tiling, which is to take advantage of data reuse. So if we look at the output if we're looking back, now we're back in our 2D stencil example. If we look at the output over here, okay, this output, the thread block processing these output elements, it's going to access these input elements over here. So you'll notice that adjacent elements in the output are going to be loading some of the same input elements. Okay, the reuse is not as much as convolution. Why? Because this element over here, okay, is only going to be accessed by the output element corresponding to this input element in stencil. In convolution, this element would have been accessed by the output element corresponding to this input, and this input. So convolution does have more data reuse than stencil, but stencil still has a significant amount of data reuse. These boundary elements don't have data reuse. Okay, in this particular stencil, maybe other stencils they might, but in this particular stencil, these boundary points don't have data reuse, but usually these internal points do have data reuse. Okay, so the observation is that threads in the same block load some of the same input elements. So the optimization we can apply is we can load, this input that we had, we can load this input tile into shared memory. Okay, and once we load it into shared memory, we can just you can just access our neighbors and the XY and the X and Y dimension from the shared memory. Okay, in 3D it could be the X, Y, and Z dimension. Now, one observation here, which is the same observation we noticed in convolution, is that the input tile and the output tile have different dimensions. So the question is, how many threads do we launch? Okay, the challenge is the input and the output tiles have different dimensions. The output tile is input tile dimension -2, right? Because here the input tile corresponds to the output tile +1 in each direction. So the input tile dimension is the output tile dimension +2. That's 1 in each direction. Okay. So what we can do, one way to resolve this issue is to launch enough threads per block to load the input tile, and then only use a subset of those threads to compute the output tile. And this is similar to what we did with convolution. Okay, so the thread block that we launch, if this here represents the thread block that we launch, this thread block is going to the dimension of this thread block will correspond to the input dimension. Okay, and when we load the input tile, all the threads in the thread block will be active while loading. But then when we compute and store the output tile, only a subset of these threads are going to be active. And here we're going to use the internal subset. Okay, one way to do it is to use the ones in the top left. Another way to do it is to do the internal ones. With convolution, we were doing the ones in the top left, but here with stencil, we'll just do the internal ones for a change. Okay, and the same thing applies. So in 3 dimensions, if I have a thread block processing, assigned to process these output elements over here, this output cube, okay, then the thread block assigned to these output elements exhibits some data reuse. And by the way, I want to remind you that in our implementation, we are not computing these boundary elements, but I'm unable to show you what's happening inside of the cube. This is why I'm illustrating that we're computing the boundary element, but in practice, we are not. Okay, so here the thread block assigned to these output elements will need these input elements, and we'll notice that there's data reuse across them. So what we can do is we can load the input tile into shared memory, and then when we do the stencil computation, we access the values from shared memory. Okay, so having said this, let's go and do an example of that. Okay, let's go and do an example. So here, I'm going to open my code again. Now we have our block dimension used to be 8 by 8 by 8. Okay, but now we have I'm gonna do some explanations on the 2D version. Okay, now we have an output tile dimension and an input tile dimension, and the block dimension is going to correspond to the input tile dimension. Okay, so what we're going to do is we're going to define input and output tile dimension. So here I'm going to write pound define in tile dim, and that's going to be specific dimension because the block is going to have as many threads as the input tile dimension. Okay, and then we're going to define the output tile dimension. Okay, and the output tile dimension is going to correspond to the tile dimension minus 2, right? Because the input tile dimension is the input is the output plus 1 on each side. So the output is the input minus 1 on each side. Okay, so here the output tile dimension is going to be the input tile dimension minus 2. Okay, and then once we've done this, we need to come down here to the code that calls my stencil kernel. And now the number of threads per block needs to be configured according to the input tile dimension, right? Because each block needs to have enough threads to process an entire input tile dimension. Well, block dim is already the same as tile dim, so here I can leave these as block dim. Okay. However, when I the number of blocks that I need, I'm going to need enough blocks to cover all the output tiles. Okay, so when I calculate the number of blocks and the output, I'm going to use the output tile dimension, not the input tile dimension. So over rather than using block dim over here, I'm going to use the output tile dimension. Okay, and this will ensure that I have blocks to cover all of my output elements. Okay. We did the same thing in convolution, by the way, so you guys should be familiar with this from convolution. Okay, having done this, now what we'd like to do is we would like to load our input tile into shared memory. Okay, so let me go back a little bit. So here we're over here. We have identified. Well, actually, we haven't yet. So now we first want to identify what output element a thread is responsible for. To identify what output element the thread is responsible for, we're going to do block index.x times something plus thread index.x. But this time is the block dimension, and the reason is that the block dimension actually corresponds to the input tile dimension. However, when we calculate which output element a thread is responsible for, the way we need to use the output tile dimension. So, for example, here, a tile that has an x index of 1 and a z index of 1 is going to skip over out tile dim elements in the x dimension, out tile dim elements in the y dimension. It's not going to skip over in tile dim elements. Okay, so over here, rather than blockdim.z, blockdim.y, and blockdim.x, we should use the output tile dimension to determine what index a thread is responsible for. Okay, so I'm going to come down here, and I'm going to replace these with out tile dim. Okay, but then to pay attention to is that even though you know for I need to find out where my thread block starts, I need to skip over out tile dim elements for every block. Okay, thread 0, 0 in the block is actually not going to be computing this output element here. Thread 0, 0 in the block thread 0, 0 in the block is not responsible for this output element over here. Thread 0, 0 is going to be responsible for this output element, which is out of bounds, because it's going to be loading this input element. To clarify that, let me go down a little. So over here, we said that all these threads are active when they load the input tile, but then only these center threads are going to be active when we compute the output tile. So thread 0, 0 is not going to be active when I compute the output tile. Thread 0, 0 is going to be responsible for loading this input element, which corresponds to this output element. But when it computes, it's not going to be active. So when I write block index.x times out tile dim, that brings me over here to the beginning of the output tile. However, my first thread is not going to start at the beginning of the output tile. It's going to start one column before that, and one row before that, and in 3 dimensions, one depth before that. Okay, so what I need to do here is have a -1 and a -1 and a -1. Okay, is it clear why? I'm going to find the output row I'm responsible for, or the output column I'm responsible for. I'm gonna use the block index to skip over that many output tile elements. So here I'm gonna start from here. If my block index is 1, I'm gonna skip over 1 times output tile elements. So that brings me over here. Okay, and then I'm gonna add my thread index. Okay, so if I'm thread 0, 0, that puts me over here. If I'm thread 0, 1, that puts me over here, etc. And then I'm going to subtract 1, so that if I'm thread 0, 0, I'm actually not supposed to be computing this element. I'm going to subtract 1 to come here from the x dimension, and subtract 1 to come here from the y dimension. And that way, thread 1, 1 is actually the what computes this first element. Okay, my I and my j and my k. The next step is for me to load the input tile. Okay. Well, to load, I first need to declare an input tile, and I'm going to declare it in shared memory. Remember, we're putting the input tile in shared memory. So I'm going to write shared load n_s. And what are the dimensions of the input tile? Well, the input tile, remember, we are doing a 3D stencil. Okay, so my input tile is actually a 3-dimensional tile in shared memory. Okay, so 3-dimensional array. Well, I simply provide it with 3 sizes. Okay, and in this case, tile is square, so it's going to be input tile dimension in each place. So I will write n tile dim over here, and n tile dim over here, and n tile. Now I have my tile in shared memory. Okay, now that I have this tile, what I'm going to do is I'm going to load my input elements. So the input elements that are over here, I'm going to load them into this tile. And remember that the way that we defined the boundary condition this time is that the thread is the thread that is processing some output tile is going to be responsible for loading the corresponding input element. Okay, so here I, j, and k, they represent the output tile I'm responsible for, but they also represent the input tile I'm responsible for loading. So the thread that's responsible for this output element is responsible for loading this input element to the tile. Okay, so I can say write n_s, okay, of thread index.z, thread index.y, thread index.x is equal to n of my indices are I, j, and k. So I'm going to write I times n plus j times n plus k. Okay, is that clear? So now what I've done is I have taken this output tile and I have loaded it into shared memory. Now there's one thing I need to be careful about, which is that I need to make sure I don't go out of bounds. Okay, I want to make sure I don't load any elements that are out of bounds in the input tile. Okay, that's particularly important at the boundary. Notice here, I, j, and k are the indices that I use to load my input tile. So simply what I need to do is I need to make sure that I, J, and K are within the bounds of M. Okay, so that's quite simple. They have to be greater than or equal to 0, and they have to be less than N. Okay, so I'm going to do if I is greater than or equal to 0, and then N, and J is greater than or equal to 0, and J is less than N, and K is greater than or equal to 0, and K is less than N. That is when I can load the input tile. Okay, so somebody's asking a good question. Didn't we choose the internal elements to compute the output so that we don't have to do the boundary checks? You're absolutely right. I've explained to you why I'm doing this boundary check. Actually, let me go all the way back to the assumption that I made. So what we said is we're only going to be processing the internal output elements. Okay, we're only going to be processing the internal output elements so that we don't have to worry about checking the boundary when we load from the input file. Okay. Well, that still holds, right? We're not going to be processing these input elements. But so the question is, how could we be in a situation where we're trying to load an out of bounds element? Well, keep in mind that when we created a thread block to process this output tile over here, we did not just create threads for every input element, but for every output element. We also created threads to load the boundary element. Okay, so the thread that is responsible for loading this value is going to be loading this value. Sorry, I'm going to create a thread. When I create this thread block, okay, the thread that's responsible for loading this value over here for this output element is supposed to load this element over here, but there are also going to be threads. Actually, let me explain from this thread block. So here, when I have this thread block, I'm going to launch enough threads for also these output elements over here. Okay. So what that means is that there are threads over here that are responsible for loading the corresponding input element. Similarly, for this thread block, there's going to be threads that are responsible for loading this input element that's out here, but none of these exist. These don't exist. So what I'm going to do is I'm simply going to deactivate these threads so that they don't do any loading. Okay. Now, we're still not computing these output elements. So the threads responsible for this output element is only going to be loading this input element. It's not going to be computing anything. If this thread was computing anything, then I have a different boundary condition where I need to when this thread goes to try and access the element outside, it needs to load a 0 instead. So that's the boundary check that we are skipping. We're not skipping the boundary check where we have to make sure that the threads that are actually loading the input elements are within bounds. Okay. So I know it's a little bit of a nuanced difference. So maybe that's something that kind of you can think about more offline. If you didn't get it, it's fine. I think you should still be able to follow along with the code. So back to our diagram over here. What we've done, what we're trying to do is we're trying to load this 3D input tile. Okay, and this is exactly what we've done. And now, before we start computing, what we need to do is we need to load sync threads. I seem to have, for some reason, my terminal's not responding. Let me check what the problem is. Okay, now my terminal is responding. So now, after I've loaded tile, I need to wait until all the elements are available before I start computing this output tile. Okay, so I'm going to write sync threads. Okay. Okay, now that I've done sync threads, and now this code over here that that does the stencil computation needs to use shared memory instead. Now this first boundary check is still valid. I want to make sure this one checks that I'm only computing output internal output elements. But now another boundary check I need to do is make sure, let me go back, sure that only the internal threads in the thread block are active during the computation, because the other threads were only responsible for loading input elements. Okay, so the way I do that is I need to make sure that my threads are also internal threads.
Can't we just set the ghost elements to 0 in the first if when we load into the shared memory?
Well, but that would require in larger input type, and I'm trying to avoid having such a large input type because of shared memory requirement usage.
Okay.
Okay. So yeah, is I could have let actually no, I want to make sure these threads don't compute because the output element they're computing is not valid. Okay, these threads shouldn't compute. Okay, the idea of loading ghost elements corresponds to the output elements that I am to making sure that I only use the I only process output elements that are within bound in the entire grid. Here we're looking at making sure to process output elements that are within bounds of the block. Okay, my next step is to do a boundary check to make sure that only these internal threads are active. And to do that, I'm going to do if thread index.x is greater than or equal to 1 and thread index.x is less than block dim.x minus 1 and thread index.x equal to, sorry, thread index.y is greater than or equal to 1 and thread index.y is less than block dim.y minus 1 and thread index.x .z is greater than or equal to 1 and thread index.z is less than block dim.z minus 1. Okay, and it was quite long, but I hope it's clear why it's important to do this check. Okay. So now what we've done is we've made sure that only the internal elements are computing. Okay, the next step is to replace all these accesses to global memory with accesses from local shared memory. Okay, so let's do that. So my so here C0 of so this input element over here n of I jk is simply going to be replaced with n underscore s of thread index.x, thread index.y, thread index.z. Okay, because so here n underscore s of thread index.x, thread index.y, and thread index.z. Okay, and then similarly for all these other values, I'm gonna actually it's just easier for me to write these from scratch. Okay, I'm also going to use the shared memory array to load these values, but in one case, actually, oops, I made a mistake here. I'm supposed to use z, y, and x over here. Okay, so make sure not to make that mistake. Remember, the most significant dimension is the one on the left when you're accessing an array. Okay, so this is x, and then over here I'm going to do thread index.x minus 1. Thread index.x plus 1 for the neighbors in the x dimension, thread index.y minus 1, and thread index.y plus 1 for the y dimension, and then thread index.z minus 1 enter the index dot z plus 1 for the z dimension. Okay. And by doing this, we've loaded the shared memory tile, and now we are when we access for this element, we are loading the neighbors in the x and y dimension and the z dimension from the shared memory tile. And notice that this shared memory tile is its own self-contained array. So that's why we're just using threadIndex.z, threadIndex.y, and threadIndex.x to access it. Okay? Is this clear to everyone? Any questions about this code?
Professor, should we not load 0 elements, or is it taken care of by the fact that we're not considering the boundary elements?
Right. So remember, the reason is because if I go back to my simple, I am never going to I'm never computing this output tile.
Right.
So I'm
okay.
never accessing an element that is out of bounds to compute an output element.
Okay. Thank you.
So I don't need to load zeros out here because I never compute this element.
Okay.
Yeah. So it's one thing to avoid reading this element. So there's a boundary check to avoid reading this element into a tile, and then there's another boundary check to avoid actually, using such an element in a computation. The latter is avoided by not processing boundary elements. The former is the one that we need to have the boundary check. Okay, so now I've written this code. Let's run it and see the performance that we get. Okay, there's a warning. Mistake somewhere. Oh, okay. Oops. So this should not be unsigned, right? Because so remember, we made the same mistake in convolution. In the original version where we weren't dealing with tiling, it wasn't a problem for them to be unsigned. But in this case, they should not be unsigned. So it's a good thing that it warned me about that. So I'm going to compile, and I'm going to run.
Just Professor, can you explain why ijk can be less than 0?
Yes, ijk could be because when I'm processing this output tile here at the boundary. Okay, the threads that need to load the corresponding tile, the thread that loads. So here, when I'm processing this tile over here, I have a thread responsible for loading the element that corresponds to this. Similarly, when I have a thread block assigned to this block tile over here, I'm going to have a thread responsible for this input here, but this input's not in bound. So this is how a thread could be -1. Okay.
Oh, thank you.
And that's represented in over here in the kernel. This is why I added -1. That's why I subtracted 1. Okay, so the code run. Notice
It took more time.
right, it's actually slower, right? It's actually slower. Well, that's a bummer. We're expecting to get performance improvement from shared memory. Well, it seems that the benefit of using shared memory, the overhead of loading to shared memory and synchronizing and then accessing from shared memory in this case was not worth the performance improvement that we got. Okay, and let's analyze why this happened. Let's analyze what's okay. So let me skip back. Okay, so this is shared memory. We use this, and then this over here is the code that we wrote together. But we noticed that we did not get any performance of it. So what happened? Well, let's analyze the compute to memory ratio. In the original kernel, each thread did what? In the original kernel, each thread performed 8 operations. So the step involves performing 8 operations, right? You have 2 multiplications and you have 6 additions. Okay, so it's 8 operations. Okay, for every thread. Okay, and every thread loaded 7 different values that were each 4 bytes. So every thread loaded 28 bytes. So the compute to memory ratio was 0.29 ops per byte. Okay. Now in our tiled kernel, what we did is we had the threads in the block collaborate to load the input tile, and then we used this input tile to access all the elements. Okay. If my input tile size is t, okay, in this case my output tile size will be t minus 2. Each thread block is going to do operations for every thread in the output tile, but it's going to load the elements for the threads in the input tile. Okay, so every block is going to perform 8 operations times the number t minus 2 cubed, because the threads that operate are the threads corresponding to the output tile. So 8 operations times t minus 2 cubed. Okay. However, each thread block is going to load one element, but the number of each thread in the block is going to load one element, but the number of threads that load corresponds to the input file. So the number of loads that a block does is going to be 4 bytes times t. Okay, so this up here is the number of operations that a thread block performs collectively, and then this over here is the amount of data that a thread block collectively loads. So this ratio over here, if you calculate it, it comes out to t times 1 minus 2 over t cubed. Now for t equals 8, the block dimension that I chose was t equals 8. For t equals 8, this ratio becomes 0.84 ops per byte. Okay, which is a decent improvement, but the improvement is not that great actually. Okay, not that great. So I incurred all this overhead to do the tiling, but my improvement was not that great. Now what we can do is if you look at this this ratio here, if I increase t, right, this whole term that I'm subtracting decreases, so I expect that my ratio will increase. Okay, so as we increase t, we improve this ratio. So for example, if t was 32, then the ratio is going to be 1.65. So that's 2 times better than this ratio that we have over here. Okay, and the intuition behind this idea of increasing t is that the boundary elements have low data reuse. So if I increase t, I'm increasing the number of elements. I'm increasing the tile size. So I'm increasing the number of internal elements, which makes the ratio of boundary elements to internal elements less. So for example, when my thread block over here was this small, I noticed I had a lot of these boundary elements compared to my internal elements. And the internal elements are the ones that have data reuse. The boundary elements don't have data reuse. If I use a larger tile size, so if I use a big tile like this, okay, now I have many more internal elements compared to the external elements. Okay, so now I have fewer boundary elements relative to the internal elements. There's still a lot of boundary elements, but they're fewer. Okay, so can I just go to my code here, my tile size? Can I just increase block dim from 8 to something like 32?
No,
Why not?
because if you use the 16 or 32 to the power of 3 is like 32,000 threads per block.
Right, exactly. If I do 32 by 32 by 32, that's going to be 32,000 threads per block. That's way too much, right? That's beyond the maximum. So increasing the tile size, I cannot just increase the tile size. There's 2 reasons. The first reason is that the input tile size is the same as the block size, and the block size is limited by the hardware. The second reason is that if I increase my, I need more shared memory to store this tile. And what did we say about shared memory?
64 bytes.
Right.
64.
It's limited.
Kilobytes. Yeah, the shared memory is limited. So if I increase shared memory, I may run out of shared memory. And even if I don't run out of shared memory, I could underutilize I could have low occupancy. Okay. So the input tile size determines shared memory usage per hardware block, which is limited by hardware. And even if the limit for shared memory is not exceeded, if we use too much, it may hurt our occupancy. So how can we increase process an output tile that's this large without increasing the number of threads and the amount of shared memory?
We use a rectangle instead.
Thread coarsening.
Right, exactly. Thread core. So a rectangle with the same number of output elements is not really going to make a huge difference. But the idea is that we can use thread coarsening, exactly. So the solution is to use thread coarsening so that we can process a larger output tile, but without using more threads. And remember, we said thread coarsening is applied when there's a price of parallelization. Okay, and the price of parallelization is redundant loading of the boundary element. Okay, when I parallelize the different thread blocks, each thread block has all these boundary elements that are used by other thread blocks, but because I'm processing these boundary elements in separate thread blocks, I have low data reuse in these boundary elements. Okay, so by making the tile bigger, I have fewer and fewer boundary elements, so I have less redundant loading of these boundary elements. Okay, and if I use thread coarsening, I've improved on. I was able to increase the tile size, the output tile size, without increasing the number of threads, but I still need more shared memory, right? So what can I do about shared memory? Well, what we can do about shared memory is we can keep slices of the input that we need because now that we've coarsened our threads, every thread is going to be processing a particular input at every step in time, point in time. So we only need to keep the data that we need for that step. And let me show you an illustration of what I mean by that. Here we said that we have two problems. First, that the maximum number of threads per block is exceeded. And second, that the input tile requires too much shared memory, which hurts occupancy or even exceeds the limit of shared memory. So what we can do instead is we can assign enough threads for processing one plane in our output tile and loading one plane in our input tile. Okay. So now I can have a 32 by 32 by 32 output tile, because here I will only need 32 by 32 threads to process a single plane. And then what I will do is I will only, these threads, when they're processing this plane in the output tile, they only need the corresponding plane in the input tile and the plane before it and the plane after it. So these threads are only going to need this part of my input tile. So then I don't need to load this entire cube into shared memory at the same time. I can just load these elements over here. And on the first iteration, these threads will process this data. Obviously, there's also another plane that is I'm not showing in the figure. Okay. And then on the next iteration, these threads will all proceed to the next output plane, and they will load the next input plane. Okay. And the plane that was previously the next plane now becomes the current plane, and I have a new next plane, and the plane that was previously the current plane now becomes the previous plane. Okay, and then on the next iteration, these threads will go to the next plane or in the z dimension, and the planes that I will need will be the following planes in the z dimension. Okay, and then on the next iteration, they go to the final plane, and we'll process the final plane in the z dimension. Okay. I actually don't have enough time to go through the code with you. I was hoping I could, but we are short on time. So you can review this is the code for doing thread coarsening, okay, in this way. And the idea here is that I declare three shared memory arrays, one for the previous. So here in every step, I have three planes: the current plane, the previous plane, and the next plane. Okay. So I'm going to declare three arrays in shared memory: previous, current, and next. Okay. I'm going to initialize the previous and the current plane. And then on every iteration, I load the next plane. I do the stencil computation for the output plane using the current, the previous, and the next plane. And then when I'm done with that, what I do is I move the current plane to the previous plane. I move the next plane to the current plane. And on the beginning of the iteration, I load next plane again. Okay. So what that means over here, my next plane becomes my current plane on the next iteration. My current plane becomes my previous plane on the next iteration, and the only new plane that I need to load is this additional plane over here. Okay, the other two are common across iteration. Okay, so that's what down here. Now, one final note. Yes, question.
Yeah, is there no way to avoid copying like the plane itself in memory and like maybe do a trick with pointer? Like not, I don't know.
Yes, you can avoid this. So you can have 3 arrays and then have an index and do modulo 3 every time on your I. You can do something like that. But just for the sake of keeping the code easy to explain in class, I didn't do something like that. But yes, you can avoid this copy from shared memory to shared memory by doing that. But actually, we're going to do something even better than that, and you'll see what that is. Okay, so one thing you might observe is that when I throughout this code, actually let me here first. So over here, when I'm processing this output plane over here, every element in this output plane needs the corresponding x elements in the current plane in the x and the y dimension. Okay, but it only needs one element in the previous plane and one element in the next plane, which were the elements that it loaded on the previous iteration. Okay, so only the current slice is truly shared across the thread block. Okay, so across the threads in the block. The previous slice is not actually shared. Okay, if you look over here, this element over here in the previous slice, this will only be used by the output element, by this output element. So this element in the previous slice will only be used by the element responsible for this input element, or the corresponding output element. This element in the input in the previous slice will only be used by the thread responsible for this one over here, this output element over here. Same thing with next slice. This output element, this input element in the next slice will only be used by the thread responsible for this input to input index. And this input element in the next slice will only be used by the thread responsible for this input element in the index. Only the elements in the current plane are actually used by multiple threads. So for example, this input element will be used by the thread responsible for this because it's in the next y position, the next x position. And then this input element will also be used by the thread responsible for this element because it's in the same position. And this input element will also be used by the thread responsible for this element because it's in the previous x position. Okay, and this so what we can do based on this optimization is we actually only need to, since only the current plane is shared across threads, we actually only need to put the current plane in shared memory. We don't even need to put the previous and the current plane in shared memory. Where can we put them? We can put them in registers. We can save the shared memory. We can save on shared memory by putting these previous plane in registers, and then moving them to shared memory when they need to be shared. So in this iteration, when I load my next plane, I can just keep it in a register. And then on the next iteration, when this next plane becomes the current plane, that is when I put it in shared memory. And by doing that, I only need to have enough shared memory for one plane. So if we go back to the, you'll notice that this previous plane, every time I access it, I'm only using threadindex.x and threadindex.y. I never access from the previous plane something that belongs to another thread. Same thing with the next plane. This next plane, when I index it, I always use threadindex.x and threadindex.y. I never access anything from the current I never access anything in this plane that belongs to another thread. So if there's no, this is different from the current plane. In the current plane, when I access the current plane, I'm accessing threadindex.x minus 1, threadindex.x plus 1, threadindex.x, threadindex.y plus 1, threadindex.y minus 1. So I am actually sharing across threads in the current plane. But it's not the case in the previous plane and the next plane. So what I can do is, rather than allocating 3 different planes and putting the previous to the next tile in the plane, what I can do is I can just have a plane for the current element, and I can have a register for the previous value and the next value, and then I load the previous plane into a register, I load the current plane into shared memory. I load the next plane into the register. I compute. Here I use the register, and then I sync threads. Okay, and then after that, I will move the current plane from shared memory to the register for the previous plane, and then I will move the values in the next plane from the register to the current plane. So here, logically speaking, the previous plane and the next plane exist. Those tiles exist. Don't exist in shared memory. They exist in another on, and that on-chip memory is the register file, and we call this register tiling. Whenever we store a tile, so here, the registers of the different threads collectively form the tile. So the current tile is stored in shared memory. The next and the previous tiles are stored in the collective set of registers across all the threads. Okay, and this is why we call this register tiling. Okay, so what we did today is we looked at shared memory tiling, we looked at thread coarsening, and we also looked at a new kind of tiling, which is register. In fact, register tiling is not new. We've seen it before. Where have we seen register tiling? Oops, there's a glitch in the PowerPoint that gave it away. So we saw register tiling before with matrix multiplication. We just didn't realize that we did it. How did we use register tiling with matrix multiplication?
When we switch to the next iteration, the previous threads are the previous values are still conserved.
No, we overwrite the previous values in shared memory. Okay, so in register tiling, what I did is I would load my A and B tiles into shared memory, okay, and I would use them to compute the C tile. So the A and the B tiles were stored in shared memory. Where was my C tile stored? Right, somebody said in the chat. So my C tile was stored in the registers, right? Because every thread was responsible for one of these output elements in the C tile. And what it did is that it stored that sum variable in a register. So this C tile is actually stored in the collection of all the registers across all the threads in the block. So the C output tile was collectively stored in the registers of the thread. So we actually used register tiling for the C tile. We just didn't realize it. Stencil, it made it more apparent that we were using register tiling because we use the same tile, and sometimes we put that tile in shared memory, and sometimes we put that tile in registers. But we actually use register tiling all the time without even realizing it. But over here, because sometimes we put the tile in the register, and then we move it into shared memory. When it's a next tile, it goes in the register. And then when it becomes the current tile, we move it to shared memory. And then when it becomes the previous tile, we move it back to a register. This tile is moving back and forth between the registers and the shared memory. This has really emphasized the importance of register tiling as an optimization as well to save on shared memory. Okay. I was actually planning to implement with you the coarsening and show you that it does give us the performance improvement over the original version, and then also implement with you register tiling and show you that it also gives us performance improvement. But unfortunately, I was too ambitious for this lecture. I didn't realize I would not have time to do all of this. But the code is in the slide, so you're welcome to look at the code later on and maybe try to implement it yourself. Okay. And with that, that's all for today. Does anybody have any final questions?
Yes, Professor. Go ahead.
Okay, thank you. I was just wondering, why is there more space in the registers than in the shared memory? Like, why is shared memory more contended than the registers?
There's not really more space in the shared memory, could be around of the order of 64 kilobytes, maybe 96 kilobytes. The register file has 64,000 registers, but each register is 4 bytes. So yes, the register file is larger than the shared memory, and the reason is that you have many threads, and each of these threads needs a significant amount of registers. So these registers files in the GPUs are actually huge. Okay, so the insight here is that if I have something that is shared by across threads during part of the computation, but not shared by threads during other parts of the computation, I can, rather than, I have all this memory in the register file. So what I can do is I can put it in the registers when it's not being shared, and then I can put it in the shared memory when it is being shared. So this is the intuition behind register timing. Okay, did I answer your question, or was your question different?
No, it was exactly that. It was like, if we're using registers, it means there's more, like we can afford to use them more than we can afford to use shared memory. So yeah, that's
right. And so like a typical GPU has a 64K registers, and if you have 2K threads with 64K registers, that means you can afford to have around 32 registers per thread. Okay, sometimes we go over that, in which case we would underutilize, we would go below occupancy because of the registers. But in some applications, we might have less than that. If you look at code that we wrote here, we're actually not using that underneath this. So we actually have plenty of threads to spare in order for us to apply register type.
okay. Thank you very much.
Yep, you're welcome. Any other questions?
Yes, Professor, to optimize even more our tiling algorithm, why don't we change the geometry of the tile? For example, in this case, you only need 3 rows. If it's a 2D array, for example, you only need 3 rows, and that way, what you can do is to make it across a bigger a bigger section of the columns.
Yeah, you can do that. You can absolutely do that. And in fact, in practice, what people do is they do play around with the dimensions of the style. And one common approach here, I explained it to you this way because just for pedagogical reasons, but one common approach is for people to actually use a 32 by 32 thread block. And rather than just going through the style, they actually go through the entire space from beginning to end. Okay, and that gives you an even larger and larger output tile, and that gives you even better and better performance. So yes, you're absolutely right that we can play around with the dimension of this output tile in order for us to maximize or try and have as low of a ratio of boundary elements to internal elements as possible in order for us to maximize the data reuse and therefore the performance.
Okay, I see. Thank you.
Yep, you're welcome.
Professor, I have a question, but like not about the material.
Okay, so then if there are no more questions about the material, I can take your question after the lecture is over. Okay, that's all for today, and I'll see you. Bye, everyone.
Thank you. Bye.